discuss about oxidation of olefins to 1,2-diols. There are a lot of reagents for the oxidation of olefins to 1,2-diols, in which first method is Prevost oxidation, or it is called dry oxidation. What is the reagent used in Prevost oxidation? That is silver carboxylate in the presence of iodine. That is the reagent. Here, this is a cyclic compound having a multiple bond. In the presence of silver carboxylate and iodine, followed by base hydrolysis, it will convert it into transdiols. Transdiol means one OH group will be in upper phase, another OH group will be in lower phase. That is the reaction of Prevost oxidation or dry oxidation. What is the mechanism of Prevost oxidation? First step is iodination with the alkene. Alkene reacts with the iodine to form iodonium ion. That is a three-membered cyclic cation. It can form either upper phase or lower phase. This is our iodonium ion. Then in second step, iodonium ion undergoes SN2 reaction with the carboxylate anion. So here we consider iodonium ion in the upper phase. Then obviously the nucleophile will attack through lower phase because this reaction follows SN2 mechanism. So here O C double bond O R will substitute and this bond will shift to iodine and we get this structure. Then it follows an intramolecular SN2 attack. That is, the lone pair of electrons present in C double bond O will attacks on carbon and iodine getting eliminated as I minus. Then what will be the product? Here this attack is also SN2, so it will attacks through sterically free phase, which means it will attacks through lower phase. Then we get a product like this. Here both the groups are in lower phase. And the lone pair of electrons lost for oxygen and it is getting positively charged. In the next step, double bond will shift to this oxygen and carbon getting positively charged. And that is the structure. Then it will undergoes another intermolecular SN2 attack of carboxylate anion. It will attacks to this carbon and this bond will breaks to this bond. So since it is SN2 attack, this carboxylate anion will attacks through upper phase. So we get a product like this. Here OCOR is in upper phase and this OCO are in lower phase. And this product will undergo saponification, that is our base hydrolysis. It will converted into transdiol. One OH group in upper phase and another OH group in lower phase. So the important point to notice that the SN2 reaction follows through sterically free side. Then we get this transdiol as product. Then another type of oxidation is Woodward oxidation, or it is called a wet oxidation. What are the reagents? Silver carboxylate in the presence of iodine and aqueous acetic acid, ACOH. That is our acetic acid. Here the aqueous medium is used for the oxidation of alkene. That's why it is called a wet oxidation. Whereas in the case of Prevost oxidation, we are not using any aqueous medium for the oxidation step. So it is called a dry oxidation. Whereas Woodward oxidation is wet oxidation. Followed by saponification, it will converted into cis diol or syn diol. Both the OH group will be in same phase, either upper phase or lower phase. That is our Woodward oxidation reaction. Then consider the mechanism of Woodward oxidation. Here also the first step is iodination using iodine, and it will forms iodonium ion either in upper phase or in lower phase. Here we select upper phase iodonium ion. Then second step is SN2 attack of carboxylate anion. Obviously, this nucleophile attacks through sterically free phase, that is through lower phase. And this bond will shift to iodine and we get a structure like this. Another step is intramolecular SN2 reaction. This lone pair of electrons attacks on this carbon and iodine getting eliminated as I minus. That is also an SN2 attack. So it will attack through sterically free phase, that is through lower phase. So we get a product like this. Then double bond will shift to oxygen and we get a carbocation. Here we use aqueous medium. So water as nucleophile attacks on this carbocation and it will converted into this structure. OH group will substitute in this carbon. In the next step, this bond will shift to this bond and carbon to oxygen bond will break. Then we get O, C, double bond O, R, and here O minus, which will be protonated using this hydrogen, and we get a structure like this. Then the last step is saponification or base hydrolysis. It will converted into diol and it will be cis diol. Consider this reaction. It will undergo Prevost oxidation and Woodward oxidation. What will be the products? Here, the first step is iodination step. In the Prevost mechanism, we can write the first step is formation of iodonium ion, and obviously it will be in lower phase due to the presence of CH3 group in upper phase, and it is a decalin. Here CH3 group in axial position and this bond in equatorial position. The positions are 1, 2, 3. 1, 3 trans. In the case of consider or imagine a decalin in which 1, 3 trans is axial equatorial geometry, and this is 1, 4 position, 1, 4 position, 1, 4 trans position, 1, 4 trans will be axial. In the second step, it will undergoes nucleophilic attack of carboxylate anion. Carboxylate anion will attacks only through equatorial position, not through axial position. So it will attacks through this side and it will be through upper phase since it is a SN2 attack. So we get this structure and it will undergoes intramolecular SN2 attack and it will convert it into this structure, and both the bonds are in upper phase. Then next step is another SN2 attack of RCO minus. Obviously it will be through equatorial position. Then which will be equatorial? This or this. Here 1, 3 position, 1, 3 cis. 1, 3 cis means they are axial. This is 1, 4. 1, 4 cis. That is axial equatorial position. Here this is our equatorial position. So obviously RCO minus will attacks through this side and this bond will breaks to oxygen, carbon to oxygen bond, and we get a structure like this. Here this nucleophile attacks through sterically free side, that is through lower phase, and we get a structure like this. And the last step is saponification. It will convert it into trans diol, and this will be the structure of the product in the case of Prevost oxidation, whereas this will be the structure of product in the case of Woodward oxidation. The difference between Prevost and Woodward oxidation is in the case of Woodward oxidation, there is an attack of water instead of attack of RCO minus. So we get a product like this. From these results, we can say that Woodward hydroxylation takes place from sterically crowded phase of olefin. Here CH3 group is in upper phase and both the OH group is in upper phase. So Woodward oxidation will take place from sterically crowded phase of olefin, whereas Prevost oxidation will take place through sterically free side of the olefin, that is based on our SN2 attack. Another reagent used for the oxidation of olefin is osmium tetroxide. This is the structure of osmium tetroxide. It will finally, after the oxidation, it will converted into osmic acid. This is the structure of osmic acid. What is the application of osmium tetroxide? Olefin will converted into 1,2-diol and it will be cis-diol. What is the mechanism of osmium tetroxide oxidation? The first step is a 2pi cycloaddition reaction and it will convert it into a 4-membered cyclic ring compound. This is the structure. Then second step, this bond will attacks on this oxygen and this bond will shifts to osmium. It will converted into osmate ester. Then the last step is decomposition of osmate ester. Different reagents can be used for this decomposition. For example, bisulfite in the presence of pyridine, bisulfite in the presence of aqueous alcohol, mannitol in the presence of potassium hydroxide, KClO3 in the presence of acid, lithium aluminum hydride or sulfide solution, etc. are the reagents used for the decomposition of the osmate ester. Then by decomposing this ester, it will convert it into our cis-diol and osmic acid as a byproduct. That is the mechanism of osmium tetroxide oxidation. And it is highly expensive reagent and little toxic. So it can't be used in large quantities. In order to decrease osmium tetroxide quantity in oxidation, in addition to osmium tetroxide, other cheaper oxidizing agents are also used. These oxidizing agents are called co-oxidants. The role of co-oxidant is to convert osmic acid into osmium tetroxide. Examples for co-oxidants are KClO3, barium chlorate, hydrogen peroxide, etc. Then to accelerate the rate of osmium tetroxide oxidation, tertiary amines can be used as catalysts. Then another reagent used in osmium tetroxide oxidation is ascorbic acid or alkaline formaldehyde, etc. These reagents are used to stop over oxidation in osmium tetroxide oxidation. So we use some of these reducing agents in combination with our osmium tetroxide to reduce its over oxidation. Otherwise, it will oxidized into carbonyl compounds and followed by it will converted into carboxylic acids. To prevent such an over oxidation, you will add some of the reducing agents like ascorbic acid and formaldehyde, etc. Osmium tetroxide hydroxylation is from sterically free phase of olefin, whereas Woodward hydroxylation is from sterically crowded side of the olefin. That is the difference between Woodward hydroxylation and osmium tetroxide oxidation. Another reagent used for this oxidation is KMnO4. Olefin in the presence of KMnO4 converted into syn diol, just like our osmium tetroxide. Then what are the limitations of KMnO4 oxidation? KMnO4, we know that KMnO4 is soluble in water, but majority of olefins are soluble in organic solvents. Therefore, for oxidation of all types of alkenes, KMnO4 is not a good oxidizing agent. In order to perform KMnO4 oxidation with alkene, phase transfer catalysts must be used. For example, alkyl ammonium, phosphonium salts, or crown ethers, etc. What is phase transfer catalyst? PTC. The substance which transfer groups from one phase to other phase. That is organic phase to aqueous or aqueous phase to organic medium. This type of conversion possible substances are known as phase transfer catalysts. They enhance the rate of the reaction and yield of the product. KMnO4 oxidation are performed in neutral, acidic or basic medium. But basic medium is the most preferred medium for diol formation. In neutral and acidic medium, over oxidation product will be obtained. That is, this is an olefin in the presence of basic medium. KMnO4 oxidize this olefin into diol, whereas in the acidic medium we get over oxidized product like carbonyl compounds and carboxylic acids, etc. What is the mechanism of KMnO4 oxidation? This is our olefin. This is our KMnO4. This is MnO4 minus. this bond will shifts to this carbon, and this double bond will shifts to oxygen, and this bond will shifts to manganese. It will converted into this compound, and it will undergoes the substitution of OH group to manganese. This manganese to oxygen bond will breaks into oxygen, and it will converted into this structure. And this negative charge attacks this H plus. This bond will breaks to this bond, and manganese to oxygen bond leave into oxygen. What will be the product? It will convert it into our syn diol and MnO3 minus. That is the mechanism of KMnO4 oxidation. And KMnO4 oxidation occurs at a sterically free phase. For example, this is an olefin. In the presence of KMnO4 base PTC, that is phase transfer catalyst, it will convert it into 1,2-diol, and it will be in endo position. Since this is our steric hindrance area, so the product will be endo. That's all about oxidation of olefins to 1,2-diols. Hope it is clear. Thank you.